Okay, we're going to begin Chapter 5, Thermochemistry. And this chapter will be all about heat. That's what the prefix here, thermo, or the first part of this word, indicates. Turns out that a major feature of many reactions, chemical reactions, is the release or absorption of heat. And we will take an in-depth study of how heat relates to chemical reactions in this chapter. In order to talk about heat, and because heat is a form of energy, we'll have to say a few things about energy in general, and specifically about two forms of energy, work and heat. It turns out that chemical reactions can actually absorb or release work, if you could think of it that way, and heat, these two forms of energy. So the first one we'll take a look at is work, and by definition, energy used to cause an object that has a mass to move is called work. So anytime there's a mass and you move that mass through a distance, you are doing work, which requires energy. From physics, this is the equation for work. We're not going to really do much with this equation here, but it's force times distance. And the important thing is you have to move an object through a distance in order for it to be called work. More pertinent to our study will be heat. And here it says energy used to cause the temperature of an object to rise is called heat. And really heat is related to the kinetic motion of molecules or atoms. So it's really how fast the molecules are moving. That's where heat comes. So a quick look at how we would measure work in a chemical reaction. Many chemical reactions actually produce a gas. A very simple chemical reaction is zinc, metal, reacting with a solution of hydrochloric acid. In this case, your product will be hydrogen gas. And in this case, what you'll see, so here is the reaction itself. Zinc plus HCl. You get yourself zinc chloride, zinc 2 chloride, and hydrogen gas. This will be the reaction. So because hydrogen is a gas, we can actually talk about this reaction having a potential to produce some work for us. And the way that's done is actually it turns out we're going to try to somehow close the system, in this case, and then put a piston in place, and this piston essentially is a movable disc. That the movement of this disc that occurs here can then be related to work. So we can measure the distance that was moved and the force that was applied and measure how much work this chemical reaction produced. That's kind of the setup. We're really not going to do too much with work, but this is how you would measure work. This is especially important, say, in automobile engines. In fact, one of the reasons why we use gasoline in automobiles is because that gasoline can be transformed into work and cause the car to move. So this is actually a very important portion of chemistry. So there are two general forms of energy. Now there's the potential energy, and this is also more from physics, but the energy an object possesses because of its position, or in our case, chemical composition. And then kinetic energy is essentially the energy of motion. So an example here would be a cyclist at the top of a hill has a lot of potential energy, and that potential energy is actually converted into kinetic energy as that cyclist comes down the hill. The equation for kinetic energy, that's actually important to us here, is kinetic energy is 1/2 mv squared. M is the mass, v is the velocity. So the kinetic energy of an object depends both on mass and on its speed, velocity in this case. The units of energy then, the SI units that's used all over science, is called the joule, with a capital J. And the joule breaks down into kilograms meters squared per second squared. And where that comes from, essentially, is from the kinetic energy equation on the previous page. Kinetic energy is 1/2 mv squared. So your mass, in this case, is kilograms. Your v squared, velocity, is actually meters per second, how fast you're moving. And since it's squared, you got meters squared, you got seconds squared. Another older, but still very widely used, a unit of energy is the calorie. And a calorie and a joule are related in this manner, and this is actually a very interesting and important relationship that we'll see. We'll see this number come up again later on. Now, anytime you take a look at a can of soda or any sort of food item, it'll say calories on the back, the amount of energy that food contains, and they're actually using a calorie that we're talking about here, except their calorie is a big C, and a big C is essentially 1,000 of these smaller calories. So you can actually convert the amount of calories in a candy bar at 2 joules. We can actually determine how many joules there are in a candy bar. So we've kind of mentioned this. Energy could be converted from potential up here to kinetic as the cyclist comes down, and for us, this is important, we're actually able to do this with chemical reactions. So you can have a mixture, for example, of a fuel, say an oxygen, and that fuel has a bunch of potential energy stored in it. And once you ignite the fuel, that potential energy is released as kinetic energy. That's essentially, that would be, for example, if you set off some sort of combustion reaction. It's very easily seen how that works. And that potential energy essentially is stored in the chemical bonds of that substance that is later released. So some more definitions. We have to define what's called a system and the surroundings, as we're going to study this transfer of energy between the reactants and products. So a system essentially includes all your molecules, and then the surroundings, everything else, including the outside world, including this piston, including this cylinder and the walls of the cylinder, and so forth. So really, the system is only what's inside. The chemicals are the system. First law of thermodynamics is important here, and then which states that energy is neither created nor destroyed. So the total energy of the universe is constant, but we're constantly changing energy from one form to another. And when we're changing it from one form to another, we can study the system, and we can say that the system loses a bunch of energy, and the surroundings gain that energy. But because the system and the surroundings are both part of the universe itself, the energy of the universe is constant, does not change. So the first thing we'll define here to work with this a little more in detail is internal energy. So the internal energy of a system is the sum of all the kinetic and potential energies of all the components of the system, and we'll designate internal energy as E, as is appropriate, big E for energy, internal energy. So then we can also say the change in energy of the system, the change in, just kind of like this little delta actually means change in chemistry or in science, and the change essentially is going from the initial to the final conditions. So then to find that change, we would take the final minus the initial. You may be aware of how delta T, you may have heard how the change in temperature, for example, say if we began at 13 degrees Celsius and then ended up at 43 degrees Celsius. To find the change in temperature, we would do the final, the 43 minus the initial, the 13, and then get ourselves 30 degrees Celsius, and that'd be our change in temperature. And we can apply this delta to really any other idea. In this case, we're applying it to change in energy. So what we'll say is if the change in energy is, if the final amount of energy is greater than the initial, that means energy was put into the system. The system absorbed energy because its final energy is more than what it had to begin with. And we designate this a few ways. We can say delta E is greater than 0. The change in energy is greater than 0. So our change in energy is positive. In other words, we absorbed energy. And the technical term for this is endergonic. If the opposite is true, if the final energy is less than the initial, we'll say the change in energy is less than 0, it's negative. In other words, the system lost energy because the final is less. We call this exergonic. So because we said that energy, in our case, chemical reactions, can release and really exchange energy in two ways, through work and through heat, we're going to give an equation here now. So for heat, we've decided to use the small letter Q, which is a bit strange, but we kind of ran out of letters. So, and for work, we're going to use W. So you can say the change in internal energy takes into account both the heat and the work. So a chemical reaction usually releases a lot of heat, but if you have a combustion reaction, that releases heat and work, and we want to be able to take both these into account. Some chemical reactions, there's really not much work going on, mostly heat. and some you got both going on. But the change in internal energy has to consider both of these. So we can now break down heat and work. So anytime the change for heat is positive, and really for any of these, if the change of the system is positive, that means the system gained that energy. In this case, if Q is positive, that means it gained heat. If Q is negative, and that means it loses heat. If work is positive, that means in a strange way it gained work, or work was done on the system by the surroundings. If work is negative, that means the work was done by the system on the surroundings, and we'll see this in a little more detail here. And then the overall, then we can say the overall change in energy. If it's positive, that means overall the amount of energy in the system increased, so there's a net gain of energy. If it's negative, there's a net loss of energy. So we can break now energy down into these two components, and we can talk about each component as adding heat to the system or releasing heat from the system. Okay, so we're actually coming up on our first example here, and really the first portion of these notes aren't very extensive. It's essentially a little bit of accounting between energies. So let's go ahead and tackle this first question. Calculate the change in the internal energy of the system for a process in which the system absorbs 1.40 kilojoules of heat from the surroundings and does 85 joules of work on the surroundings. So really what we'll do is we'll take our equation, which says that the change in energy involves heat and work. Now, because we're told that the system absorbs 1.40 kilojoules of heat from the surroundings, that means our heat component will be positive because the system absorbs that heat. Anytime it absorbs, that would be positive. So we got Q is positive 1.40 kilojoules, and then it says that the system does 85 joules of work on the surroundings. So our work is actually going to be negative 85 joules. And the reason it's negative is because the system did work on the surroundings. It pushed against the surroundings, which in a way you can think of it released work to the surroundings. So really it's a matter of simply adding these two up. Now, and before we add them up, we have to put them in similar units. So we can either convert the heat component to joules or the work component to kilojoules. So customarily kilojoules is what we usually report most of these in. So why don't we convert the joules to kilojoules? So let's go ahead and convert negative 85 joules into kilojoules. And just like we would do with kilograms to grams, we know that joules would have to go on the bottom, kilojoules would have to go on top. The prefix kilo means 1,000, so 1 kilojoule is 1,000 joules, just like 1 kilogram is 1,000 grams. And then dividing by 1,000 essentially is moving the decimal place left 3 times, so we get ourselves negative 0.085 kilojoules. Now that we have both of our values in kilojoules, we can simply combine them. So what you've got yourself here is you've got yourself delta E, change in internal energy, is equal to 1.40 kilojoules minus 0.085 kilojoules. And if we subtract those out, we should get an answer that looks pretty close to 315 kilojoules. Is that right? Looks like that's how much we've got. And so for the purposes of significant figures, it looks like when we're adding or subtracting, we go by the least number of decimal places. And because our decimal place, the hundreds here limit us, we'll essentially have to kind of finish here. So for the purpose of significant figures, let's go ahead and say 1.32, we'll round up, kilojoules for our answer. This is the change in energy of the system. Pretty simple problem. Just add up the heat component and the work component, put them together. So a few more theoretical considerations here. Usually we have no way of knowing the exact internal energy of a system. So say you have yourself a cup of water, and pretend it's well, here we'll say it's at 25 degrees Celsius, this cup of water, room temperature. And if somebody asks, well, how much energy is inside of here? It's actually very difficult to calculate. And in our case, we're actually not going to calculate how much energy is in here. What we will calculate is, well, if we heat up a bunch of water, then what's going to be the change in energy, say from this to this side, or from this side to this side, or from here to here. It's much more easily to talk about the change in energy. As we'll see, we don't really care about how much exactly is in here. We care about how much it changed by. Say, because our chemical reaction is about to release a bunch of heat. We don't care as much, well, how much energy did the chemical reaction have inside of it, but we do care about how much it released, because that's, we'd like to warm our house, we'd like to power our car with that released energy. So really we're going to take a look at this change. That's really what's going to concern us here. Now, we're going to actually define enthalpy and work with something called enthalpy from now on. And here it says that the reactions we'll study involve, many of the reactions involve only a heat change. And because we're going to be working with open vessels, we're not going to allow the pressure to build up, and so there'll be no work done by our reactions. In other words, we're going to study the heat component of the reaction and not really the work component of the reaction, even though that's also an interesting study. So we'll call the heat component enthalpy. And this is actually an old word related probably to the Latin or the Greek version of heat, enthalpy. And we'll use capital H for the heat change. So actually, from this point on, we're going to drop delta E. We're not going to talk about it too much more. Remember, delta E has both a heat and work in it. What we're going to do is we're going to single out heat from now on. And so we're going to change from delta E, which has both of these, to just delta H, which has just the heat component. And essentially, that's going to be it for now, for the first lesson here. We'll take a look at the heat component starting with the next lecture.